And it was a pretty specific task. It says, well, you have to look at the high priority challenges in key areas of research so that we better understand the space environment, so that we have a demonstrable improvement of timely and reliable information that is relevant to the civilian space and ground-based systems all around the world. That's quite a challenge to work on. What we do is we look through, and I'll show you examples of how we got there, all of the particular choices one can make about where to put investments, intellectual and financial and political. What do we do on the short time scale, on the intermediate time scale, the long time scale? And where do we see gaps? Where do we see opportunities to work with? And by the way, I do have to define space weather. For us, when we were talking about space weather in the context of this particular charge, it had to do with the Sun-Earth connections. So really everything that had to do with the variable state of the coupled space environment related to the changing conditions on the Sun. So we're not talking about space debris, we're not talking about asteroid impacts, we're really focusing on essentially this electromagnetic coupling that exists between the Sun and the Earth. We have had a few meetings, we're going to have one more a few weeks from now to really write things up. We've had discussions at different forums, we've been to the European and US Space Weather Weeks, we've talked to officials at various agencies, and we've sought for community input. One of the reasons to be here is, again, to do this. This is a draft. We want to hear from you, what you think about this. We need to have comments from every one of the stakeholders, the science, the politicians, the insurance industry, etc., the space weather service providers. And then we're going to have to compare to the plans, see where we complement and where we advance, and then integrate everything into a written report. Now, we've basically gone through these different impact pathways. We've listened to the space weather users and say, what is it that you need? This is just an example. I'm going to go through this fairly rapidly. You can read about this, we'll put this on the web or make it available, or we can come back to it in the discussion sessions and say, what's the most important thing here? Well, it turns out that different sectors of society, different parts of this entire arena of space weather have different interests, different primary needs. That in fact, if you look at these three different impact pathways from electrical systems, navigation, and aerospace assets, space assets largely, but also airline industry is of course concerned about its passengers, its crews, and about its microelectronics increasingly flown on these things. That in one case you might just primarily need to engineer to it because you can't move things out of the way. In other cases you have a need for a rapid dissemination of near-term information, nowcast information. Or you want at least a day ahead of time that information. For example, the power grid companies would really like to know, they need to know a day ahead of time whether a geomagnetic storm is going to occur, because they have to position their networks to be able to respond to this. They have to pre-purchase power, they have to make sure that the long transmissions are limited. So they want to know things a day ahead of time, and that has consequences. The example here is, if you say you need to know a CME is coming more than a day ahead of time, L1 monitoring may be your last warning, but you need to go beyond that, and because practically and financially we can't put spacecraft literally between the Sun and the Earth at present, it means we suddenly find ourselves at what leaves the Sun. So we went through all of that, we filled many tables that we can look at in some detail, and in the end we said, this is what we're going to do. We're going to look at these three impact pathways and ask, what does it take for a 2-day forecast, an hour forecast, or looking backwards, what do we need to get out of archives that exist, or the really historical archives about extreme event conditions. We have, I'm going to skip these, we have, by doing that, basically been able to identify where the primary needs lie for these sectors. Wherever it's red, that particular pathway has to get its information in order to create a forecast, or a nowcast, or a hindcast, an extreme event condition. And on top of that, we then say, well, these are the boxes that we need to fill. We need to know these things. Again, I'm not going to read these to you. You will understand them when I get to the last few slides in this presentation. But once we do that, we can then say, well, what is it really that we're asking? We're asking what leaves the Sun, what happens to it before it gets to the Earth, what happens in geospace, what does that do to our technology, and how does society respond? And each one of these, interestingly, we have realized, we as a community, not just this group of us looking at this particular problem, that there's a lot of hysteresis and preconditioning in the system. Event studies are interesting, but because we have this highly nonlinear system, we have to know the continual stream, not just look at the event. What came before will affect what came after, even in society. What society does about space weather will depend on what information we provide and what happens to societal infrastructure. So, we've taken these impact pathways and identified amongst them what we think are priorities. Now it's an odd word, I still don't know what word to use. Priority really is a mix of, it's important we know scientifically, it's important we know practically, and it's feasible that we can do this, and we have to do certain things before we can do other things. So all of that is folded into what becomes a priority. We've identified opportunities, we've identified challenges, and one of the challenges is putting all this in a readable document. But the bottom line is this: we can distill out of this a set of recommendations. So here's a set of recommendations. I'm going to go through two nested levels. One is really high level, one is particularly focused on what here are the second and third bullets in this particular slide. One is we really have to move our research into focusing on the real world. That seems a fairly obvious statement, but it's a difficult thing to do, because what it means is for all of the sciences related to space weather, from sun into geospace, into our technology, we have to be able to develop data-driven and data assimilation models. And we're not doing well enough on that in the present-day capabilities. If we wish to understand enough that we can forecast, for example, a day ahead what coronal mass ejection is going to do to geospace, we have to really understand the solar origins, and in particular the post-eruption modeling. That sounds kind of interesting. You don't have to predict the flare or the eruption, but you have to predict what is going to get to Earth. That buys us some time. We can look at the event that's already happened before we have to make the forecast and before the event reaches the Earth, which is not to say flare forecasting isn't important. I'll come back to that in just a moment. And once we've done that, you really have to know, of course, what is geospace going to do with that signal coming to us. So we have to understand how the magnetospheric field is going to respond to a driver from the solar wind and to its internal processes. And we have to develop space climate specification and forecast tools. We really have to be able to say, this is, for your particular technology, the kind of environment it's going to be operating in. You'll be susceptible to these kinds of perturbations for this much of the time, and sometimes it can get this bad. That needs a lot of work because we don't nearly know enough about those specifications yet. The second has to do more about how you implement this kind of research. How do you create this collaborative research environment between the various societal sectors that are impacted? Well, one is, we think it's very important that we quantify vulnerability. And that has to be something that is done in a collaborative effort between the scientists and the users of space weather information. In many cases, I'm stressing this particularly because in many cases what will happen is if we ask for what is the vulnerability of electric power grid, you'll get concerns of national security, you'll get concerns about proprietary information, you'll get concerns about liability. If you talk about the internet infrastructure that we have, if we talk about the GPS navigation systems, the impacts on satellite systems, you get similar barriers every time you ask about that kind of question. We can create a structure, we need to create a structure in which the information flow becomes bi-directional. Not just information going to, but coming from the impacted sectors, because the impacted sectors have to tell us as scientists where to put our resources, where the biggest difference can be made if we study these things. We should really develop focused opportunities for observations and models. What does that mean? That means there are places in the world where, for example, ionospheric studies are being done with particularly capable instrumentation. It makes sense to focus more observational capabilities there. When we look at the sun, it makes sense to coordinate observations from various perspectives and not to have one perspective come after another after another. When we talk about modeling endeavors, we really have to work on creating models that are data-driven, data assimilation models that are no longer simple. They're not, we cannot do these by having even the most brilliant team of postdocs work on it for just a few months of the year. These are big efforts, and we have to focus on that kind of capabilities. We have to standardize the data and the data product metrics, because more and more our computers are doing the data searching and the data coupling for us. And if we don't standardize, if we don't open things up in a particular way that they can all understand what it is that we're looking for, it's going to be increasingly difficult. The amount of data and the number of data environments that we're dealing with is growing very, very rapidly. And then, of course, we have to really optimize coverage. We have a vast space to cover. Literally big. Big, humongous in terms of physical scales, but even just big to think about. We have to be able to combine observations with data-driven models to create a full understanding of the world that we live in. We have to optimize data flows by using existing ground-based and space-based resources. And above all, we have to be much more sensible about how we spend our limited resources. We have to learn to develop affordable new instruments. Instruments that don't, when you think about an observatory on the ground or an observatory in space, that one instrument does not have to solve the problems of the universe. That instrument can be thought of as an essential additional component into an observatory that's already there and observing, but to which that new instrument offers a very important new capability that enables us to do things we could not do before. That might make it more affordable so that we can fly more of these things and put more of these observatories on the ground. Now, I'm going to switch to a few slides that have an enormous amount of words on them. And I apologize for that in a sense because it's very difficult to read through it. If you don't want to read it, just listen to my voice. That might make it slightly easier. But there's really a lot of things that we're doing. And what we're going to be doing is write up those... sorry, I have to go back to this one. Another important set of recommendations is a set of recommendations that has to do with the general environment in which we work, that really involve the coupling between society, agencies, governments, and the scientists. It's important that we work on an open space weather data and information policy. It's important that we identify and provide access to quality education and information materials. Do you remember 140,000 web pages just last year that had to do with space weather? How are you going to find what you need? Where are you going to find the information that you need to talk to a colleague? Where do you find your educational material from which you say, now I understand why this works in a particular way? Where do you find the information about a particular impact pathway of space weather? It seems that that information already exists. Finding it is the problem. So some effort on developing channels, hubs towards that information would be very valuable. We've learned that doing this exercise is something that probably is worth doing every couple of years. Not every decade, that's too slow. Not every 2 years, that would be too fast. So maybe every 5 years you do this again, because technology changes, our physical realities change, our scientific understanding changes. We really need to also focus on developing the environments that can transition research tool to operations. It isn't an automatic thing. It's something that really requires attention and dedication and expertise in order to take something that we define as a research tool to become something that's reliable enough to become an operational tool. But that's the important leap that we need to make in order to make space weather information usable to the community and the world at large. And it seems that we really should look at the weather and climate stakeholders. There's a lot of information we can learn from them about data assimilation and data-driven techniques. They have a vast network of infrastructure for data distribution that we can learn from and maybe even use. They have sites on which we might put observatories that have something to do with, say, with ionospheric variations or geomagnetic disturbances that are already there that we can learn from. And they also have ensemble modeling and the development of forecasts and their standards based on that from which we can learn lessons. So there's an interesting and very important partner that we need to start looking to far more intensely than we have until now. So, these promised text with lots of words, because now we have to be specific. Those were too generic to really act on. If I look at our customers, which are the space agencies and the science agencies, they're going to go, well, what do you want us to do? Well, so let's get specific about this. And we're going to recommend these in sort of 3 tiers. Tiers because they really are this, the bottom green text says it, the merged weighting based on what we think can be done, what the scientific need is, what the estimated feasibility is, the likelihood of actually succeeding in something, and of course you have to do certain steps before you can get to the next step, the tiers. The steps are this step. I have to take the first one before I can get to the top one. in that sense, we're going through this in this way. First has to do primarily with impacts of geomagnetic disturbances and the consequences of geomagnetically induced currents on electrical systems beyond the one-day forecast. That really says we need to know what has left the sun, is on its way to the Earth to do something to our infrastructure here. And that also drives variability in the ionosphere. Once it gets here, it drives variability in the energetic particle environment. So that's the first step you take. Then you get to the second tier, which is really about the particle environments that specifically affect aerospace assets. The hardest one of all is to say what will happen before it's even started to happen. When will a flare and a coronal mass ejection occur on the sun? In what direction will it go, and what's the magnitude going to be? So that from there we can cascade it through all of our newly developed modeling and theoretical capabilities to create this final forecast. So, more and more words. Now, I'll talk you through them in the remaining 10 minutes or so. We've basically taken every one of these tiers and said there are three categories in which we can think about this. The first is, in a sense, the easiest. Some things you just have to keep doing. You're already doing them, but if we discontinued them, there'd be a gap in our abilities. The second is not intellectually easy. It'll be quite challenging, but financially and pragmatically fairly straightforward to implement on a short time scale. Whenever we talk about things that have to do with archival research, with data infrastructures, or with modeling capabilities, we could start these now or in the very near term. When we talk about new instrumentation, which will show up on the next slide, that typically has a much longer lead time, of course. So, given these three types of categories, in each of which there is a prioritization, we'd say, well, this is what we need. In order to be able to provide useful space weather information to the forecasters, the service providers, and the eventual users in society, we really need to maintain our ability to know the solar surface magnetic field. We need to know the UV and X-ray imagery of the sun, because that's what drives whatever happens through the heliosphere into geospace. We need to maintain coronagraphy. We now have it from multiple perspectives, with the stereo spacecraft and spacecraft floating upstream of Earth, and sometimes from ground-based observatories. But we need to make sure that we maintain that ability, because that's the ultimate warning that there is a coronal mass ejection and in which direction it's happening. We need to maintain the ability to do in situ measurements of the solar wind, because that's really the last step before it happens. But it really is the driver of the geospace environment. So any model that we have to develop for the geospace environment has to start with what comes into it, in terms of photons from the sun and in terms of wind from and around L1, somewhere upstream of the Earth measurement. For some years it seems very sensible to continue the interaction across the bow shock and the magnetopause. There's a lot to learn still about how the solar wind couples into the magnetosphere across that interface, and right now we have a number of instruments looking at that. It's well worth maintaining those for a few years to come. And then of course there are more ground-based sensors that complement satellite data. We'll have to be more specific in our writings, but it can't list everything in just a few minutes here.